So let me introduce the next speaker. So our next speaker is Matt Williams. He is a field CDO at Cornelis Networks with nearly 30 years of experience driving innovation in AI, HPC, and high-performance data centers. He is a former CDO, founder, and inventor, with 23 US patents, and he has shaped 5 generations of networking architectures. Matt, thanks for being with us, and the stage is yours.
Well, thanks, Artem. I really appreciate the opportunity to chat. So today, talking about reimagining a scale and architecture for HPC and AI, and I am the field CTO for Cornelis Networks. Now, I'm not sure how many people are familiar with Cornelis, so I thought I'd quickly cover off who we are in a nutshell. We are the inventors of OmniPath, which was created at Intel with a focus on meeting the challenges of high-performance applications. And really, that's all about lowest possible latency, highest possible message rate, and being able to use the bandwidth available as efficiently as possible. It was based on QLogic and Cray supercomputer technologies and spun out as an independent company a few years ago. We're about 230 people, and we all have deep HPC expertise and a truly maniacal focus on application performance. We understand that the network is the bottleneck for HPC and AI. As Amin mentioned, a lot of the applications today, whether it's AI training or large scientific workloads, they don't fit on a single node. They don't fit on a single CPU or GPU. And so what you need to do is thread that application across multiple nodes. And then the problem is, well, how do you share information across those nodes? That's the network. And for many applications, if you have a slow network, the application is just not going to perform well. So having a network that's focused on the needs of HPC and AI is critical if you want to get the efficiency out of your application. And efficiency is not just a sort of time to results problem, it's an energy efficiency problem. It's a how well am I using the capital in my infrastructure problem? So it's widespread. And I'm very happy and very proud to report we have a network solution with the lowest latency and the highest message rate and the fastest application performance. I'll be sharing some benchmarks later on. So Cornelis is an end-to-end network solution. So we have SuperNICs, we have switches, and we have integrated software. The key thing about Cornelis is we've designed this silicon ourselves. It's in-house silicon. Again, with that focus on how do I get the best possible performance for my HPC applications, my AI applications, and trying to leverage an existing technology and make it move faster can sometimes be limiting. So we designed it from sort of bottoms up to make sure everything is about performance, everything is about easily being able to deploy the solution in a data center environment. So on the SuperNIC side, it's a low profile PCI Express Gen 5. And we have 2 different switch form factors. We have a 48 port switch, it goes top of rack, middle rack. And then we have sort of unique director switch form factor, which allows up to 576 ports. That's about 36 normal switches in 17 rack units of space, consuming only half the power of the equivalent switches. So a very, very efficient deployment vehicle for sort of medium scale HPC and AI applications. And then we have optimized open source hosted management software. We are very big believers in open source, in the community, in working together on these open standards to ensure that everyone can succeed and that solutions can be deployed easily within multiple software stacks. And if you look on the bottom, just sort of a highlight to some of the performance we're seeing in early versions of our software, we're about 2.5 times the message rate and 34% lower latency than InfiniBand 400 gig NDR. And that's very, very important because the applications we're targeting, HPC, AI training, AI inference, are very, very sensitive to these metrics. And so when you look at the performance leader box here, with some HPC applications, we're seeing up to 45% higher performance, which is tremendous. If I was to tell you I could get you 10% higher performance, that would be very, very beneficial. We're getting up to 45% in some of our applications. So on the software side, just like our hardware has been designed for maximum performance, our software was co-designed to ensure that, for the things that matter in the applications we're targeting, we move as quickly as possible. So, example, for small messages, you're not talking about a bandwidth challenge, you're not talking about a bus challenge. What you're really talking about is how few CPU cycles can I use when a process wants to send data and get it out on the wire. And we have a tie to software, about half the CPU cycles of anyone else. That's a big reason behind our high performance, small message latency and message rate. We have full support for all software stacks, as you can see, SHMEM, MPI, GPU programming environments like ROCm and CUDA, high-level AI environments like PyTorch and TensorFlow, all based on our completely open source OPX libfabric provider. We also support things like verbs for I/O upper-level protocols, file systems. But the key to what we're doing is all around libfabric. And just for people that aren't aware of libfabric, it's the technology that's been chosen by Ultra Ethernet as the software stack. As we have years of experience there, we're taking a leadership position in making sure libfabric is the correct way. It's integrated very well with all the things that are going on in market. And as I said before, we are fully open source. So our libfabric provider, OPX, is fully open source. We actually upstream our kernel drivers to kernel.org. Now, that takes a bit of time for the kernel.org folks to integrate it into the kernel, but they have very strict processes to make sure it's trusted software. So when you deploy our solution in your data center, we typically are in distribution already with the driver. So very easy to deploy, full software support northbound. It really is a very trusted and high performance solution for our customers. So a little bit more about how we get our industry dominating latency and message rates. Really, we take a look at what are the needs of different kinds of messages sent between processes, whether they're MPI processes or a kernels on a GPU, whatever it happens to be. If it's a small message, really the focus, as I said before, is on how quickly can you get the message out to the hardware. So what we have is hundreds of independent parallel pipelines on our card. And a process on the CPU, as an example, at MPI rank, will be assigned one or more of these dedicated resources. And when that process wants to send a small message, it actually talks directly to the hardware, bypasses the kernel. There's no calls. It's a unidirectional, please send this message. And that ensures that that message gets to the hardware as quickly as possible. That's how we achieve a 2.5 times NDR message rate in our architecture. We have intelligent traffic arbitration, lots of QoS control, lots of support for multiple kinds of traffic. And then we have a very highly optimized packet format. Again, when you're focused on performance, you want to make sure that the whole stack is optimized that way. And having a tight packet format and a very strong physical layer ensures that we get the packets out very quickly and very densely packed. Now, with large messages, it's not efficient to have a process sort of managing that transfer itself. So what we have is 16 DMA engines on the card. When it's a large message, there's a small setup cost in setting up a DMA transfer. Then the card will take the data straight out of application memory. So it allows us to get very high efficiency on line rate bandwidth performance. And it's architected so well that we actually get the full bandwidth performance faster than anyone else. So we're lower latency, we're higher message rate, and the bandwidth efficiency is better than everyone else as well. Now, on the return path, as we're receiving packets, we have programmable packet processing engines that allow us to manage the data very effectively. And then we directly deliver the data, whether it's to the application space, if it's a rendezvous transfer. If it's an eager kind of transfer, then we deliver it to the kernel, which is then delivers the data directly to the correct application. So everything is optimized for performance, software stack, the hardware, the co-design. We make sure we get the best possible performance as moving data onto a network. Now, once you're on the network, as people have been talking about, right, how do you manage the challenges of a large-scale, congestive environment? When there's lots of applications running, it's not an easy environment to maintain performance. So this is one of the technologies we've developed. It's called FGAR, stands for fine-grained adaptive routing. And the idea is that when you're in a potentially congestive environment, the first thing you want to do is not add to the congestion. What I mean by that is you want to make sure you're spreading your traffic on as many places in the network as possible. If I was to send my heavy elephant flow down a single path, I'm guaranteed to congest everything on that path. If instead I spread it across the network, I'm going to get much better performance, not just for myself, but all the applications on the same network. So in our solution, the application through its MPI semantics or directly through libfabric semantics will let us know that out-of-order delivery is okay. For example, it's a bulk data transfer, or maybe it's a storage request, whatever it happens to be. And what the CN5000, our SuperNIC, will do is mark those packets as being able to use this advanced adaptive routing technology. And so what we've pre-programmed in this network is every single switch is pre-programmed with every potential upstream next hop. So when you're thinking of a factory, all of my spine-facing ports and leaf switch, I can use all of those. There's no restriction on how many we can support at any given time. So the switch already knows all the different ways it can use to get to the destination. Because the packet's marked for FGAR, what it does is it round robins across the best subset of those ports. Now, best is an interesting statement. It's not just which do I believe is the least congested port. It's I can see my ports. I can decide, oh, this port here is heavily loaded. I'm not going to use it right now. I might use it later. I'm going to use a different port. What we do as well, though, is we have switch-to-switch telemetry sharing. So every switch is aware of every next hop's congestive state. And so I'm looking not just at my own state of congestion, I'm looking at the next hop. So I'm very easily able to determine the best possible next hop, not just on my info, but for the rest of the network as well. Example here, if there's a congestion event on this port, the switches are always sharing telemetry, and this switch will say mid-flight. So as the packet's arriving, whereas before it may have gone down the upper path, I'm going to redirect that packet. So at every single switch hop, it's making a decision of what is the next hop. We're able to react almost in real time to any congestion that happens in the network and ensure that those packets arrive very quickly at the far end. What this does at a higher level is it ensures consistent bandwidth performance. A hotspot anywhere in the network will effectively be avoided within one hop in the network. So very, very fast performance, consistent bandwidth, very, very good for things like AI training, sharing of data, the gradients that we talked about earlier, and any kind of storage application. So advanced technology just built into the hardware, packets arrive out of order, and when they all do arrive, the process is simply notified that, hey, all the data is here. So very advanced capability. The other thing we have, which is pretty unique, is we are a layer 2 network. We don't have any kind of routing requirements at layer 3. And what we have is the ability to go to a very, very large scale in this layer 2 environment. So we have a 24-bit hierarchical lid. Now, lid is the addressing scheme OmniPath uses. It's a unique address assigned within the network. You can think of it kind of like a MAC address for Ethernet, a little more advanced technology, though. In this HLID, we can define on a per use case deployment, per customer deployment, or even per cluster deployment, what the HLID means. And what we do is we break down the HLID into multiple fields, multiple subfields. And so if I'm deployed within a tree environment, I assign different bit fields to different parts of that address scheme. So we might have some bits that indicate which pod I'm in, which tier in the network, which switch at that tier, and which port I'm using. What this allows us to do for these different kinds of topologies is support different scaling points and different performance points for these different kinds of applications that are being run by our customers. And it also allows us to have very, very compact route tables and allows us to get to 500,000 nodes within each of our switching points. So as an example, if I'm in a Dragonfly topology and I'm in a virtual routing group 7, and my packet is destined for a node in virtual routing group 6, the fact that it's in a switch 1 and port 2 is currently irrelevant. All I need to know is how to get the data to the next hop. And so I have a set of next hops. In this case, I've shown 8, that allow me to get efficiently to the correct destination. And again, using FGAR, choosing the ones that are currently least loaded from my perspective and from the next hop's perspective. So very, very advanced technology allows us to be very, very flexible in the topologies we support. So we're not stuck to just fat trees or certain dimensions of Dragonfly. Effectively, we can support any topology. The ones we're focusing initially are about tree, Dragonfly, Megaflies, and these HyperXs. So different applications require different topologies. We can support them all. The other sort of unique technology we have is called link level retry. So one of the challenges of optical networking is as the link speeds have gone up, the lane speeds have gone up, and NRZ is no longer sufficient, and PAM4 encoding is much more common. The challenge with PAM4 is because the I is so tight, you'll get a lot of bit errors on the link. Now, FEC can be used to hide some of those errors, but there's always FEC escapes, as they're called, where bit errors are seen by the network itself. And the challenge is, of course, at 400 gigabits per second, you're actually seeing a bit error every 2.5 seconds when you look at a 10 to the negative 12 bit error rate, which used to be considered good. But the kinds of applications are running now that are so sensitive to latency and bandwidth performance, this is a very serious issue. So with OmniPath, when a bit error does occur on the link, the previous switch has held on to a copy of that packet. And the next switch can simply say, hey, I received an errored packet, please retransmit it. So that sort of retransmission loop is very, very fast. It's a couple of time of flights on the link, sort of hundreds of nanoseconds of time, and we retransmit it locally. So from an end-to-end perspective, not only do we have no congestive loss as part of our architecture, but bit errors don't cause any loss either. When we compare that to other networks, the challenge is that a bit error will occur in a link, and either the next switch or the destination will say, hey, I have an errored link. I have an errored packet. I need to have a retransmission. Sorry, Artem, you have a...
Just a notice that we're approaching the end of the talk, so you have a few minutes to wrap up.
I will go quickly then. So the problem here is that the retransmission request is end-to-end. So you have to send a request to the loaded network, and that, of course, is going to load the network in order to retransmit the data. Because of these go back-end protocols, you're going to be a lot of inefficient loading of the network. And the stack will misconstrue the dropped packet as being a congestion event, even though it's just a bit error event. So a lot of times the stack will slow down. So this causes spikes in tail latency, drop in performance. It's really not good for AI and HPC applications. So I'll quickly show some of the performance we're seeing with early versions of our software. We are tuning and developing advancements on the performance side. First, we have micro benchmarks. This is ping pong latency. So for 8-byte messages, which is a common metric, we're 23% faster in this graph, up to 34% faster as you go up to 16 kilobyte messages, again, comparing to NDR and InfiniBand. For message rate, we're about 2.5 times higher. So whereas NDR caps out about 450 million messages per second bidirectionally, we get up to about 800 million messages per second. And then if you take that and apply it as an effective bandwidth, that's you scaling up a message rate or a message size, you can see that we have tremendous bandwidth efficiency advantages as well. So our bandwidth ramp is the best in the market. But the key thing that customers care about, of course, is application performance. So again, on an early version of our software, as we go for our benchmarking suites, you can say that different classes of applications, some of the applications aren't sensitive to the network, some are extremely sensitive. And in manufacturing workloads, 45% higher, physics and life sciences, 41% higher, for some climate codes up to 25% higher. And this is only on an 8-node network. So even at smaller scale, the advantages of our architecture are pretty clear. As we look at scaling performance, this is a molecular dynamics code called NAMD. You can see that with CN5000, we have almost perfect efficiency scaling. So as you go to higher and higher nodes, you get the equivalent addition in system performance. And compared that to NDR, we're about 41% higher performance on scaling molecular dynamics codes. So in summary, OmniPath has been around for several years. We have proven scalability, proven performance. As we're looking at HPC and AI workloads, we have leading application performance at any scale. Our whole architecture is based on maintaining performance at scale, avoiding the congestion challenges that Amin talked about. And this is all about maximizing the efficiency of a cluster. GPUs and these large CPU systems are expensive. You consume a lot of power. Being efficient is critical to getting more usefulness out of a cluster and being environmentally conscious as well. Thanks.
Thank you, Matt. Thank you very much. It's a really interesting talk. We hope to see you again with more updates in coming years.
Absolutely.